of everybody. And we are delighted to have you here. Our Zoom people should have just gotten the word that we're recording, which we do record the meetings. And we do that so that then we can post them and make them available later on Facebook and on YouTube. And we have our Facebook people joining us tonight, as well as our regular members. I'm May Smith. I'm the TAAA president. And we have with us tonight Jim Knoll and Terry Lappin, who are working with the technology and the Facebook. So we have a busy night tonight. We have two speakers tonight, and we also will have a vote that our members will be involved in. And so I want to let the members know that if you're online, if you're attending by Zoom, then you will get to do your vote toward the end of the meeting when we have members only. And those of you who are present at the meeting tonight, we want our members to go ahead, if they would please vote at the door when they come in, or if anyone needs to take the ballot to their seat and vote, then when you have finished voting, please raise your hand so it can be collected and all the member votes can be in, and counting can get organized on that. So thank you so much for your patience with this. For our speakers tonight, we are going to have people enter their questions who are on people who are on Zoom and people who are on Facebook. Enter your questions in writing. Our people on Zoom will be muted during the speaker presentation, but we want your questions. And so enter your questions in writing in Zoom, and then people who are attending in person, we will of course address your questions here, but you will need to wait until a microphone is delivered to you because we want everyone on Zoom to be able to hear your answer. And we cannot do that if we don't take a mic to you. But a strange contrast to that is, for those of you who are in the room, the Zoom does pick up any talking in the room, including talking at the very back of the room. So we ask that people, when we are running the meeting, that people not talk who are in the room because you will hear this. Sometimes Zoom will pick up the words and sometimes it'll just pick up noise, but it will interfere with our people on Zoom being able to hear. So we're delighted to have our Facebook people join us, and we're delighted that we can have members both on Zoom and in person. We have some really good activities tonight. We have a couple of great presentations, but I do want our members to be aware that because we have two presentations and some other things happening tonight, we are not able to have breakout rooms on the schedule tonight. We normally try to have breakout rooms so that everyone can participate in those during our member section of the meeting, but we're really not able to do that because we just got a heavy agenda otherwise. But we'll start with our first speaker, and we have Dr. Brad Schaefer, who is a TAAA member, who's going to be a speaker for us. Brad got his PhD at MIT, as you saw from the information that went out, and he has a long, nice history of doing all kinds of astronomical things. And Brad, I think, is looking for a speaker right now. Do you need it? Do you need a speaker? You're set? Okay. Okay, great, Brad. Just a minute here.
Testing. Okay. Hey, today I'm going to go talking about ordinary watching of the sun with the unaided eye from the Tucson area. Talking about a couple of the research things that me and Jim have been doing. Let me give a bit of background here. Well, down. Okay, well, went down. Anyway, what you have here is that all cultures everywhere have always had large numbers of sun watchers for a wide variety of purposes. Much of the time, it's going to be for using the sun as a practical tool. The sun's not the only, but largely the way that people in the past in all pre-modern cultures have been able to tell time, make calendars to know when to plant crops, for navigation, for direction finding. The sun is what you use. It's your go-to tool. And so every culture has a large number of sun watchers for various reasons. Also, you have various symbolic reasons. For example, with Stonehenge up there, you have, well, we aren't quite sure what the symbolic reasons are, but you have these alignments on midsummer sunrise. And actually, this is a little bit of a worry here for us, because in the last 20 years, there have been a couple different proofs, almost with a capital P, that shows that the midsummer sunrise alignment is not what's actually going on at Stonehenge. It's actually, you're looking in the opposite direction. You're looking at midwinter sunset. That's what was intended there. And you never hear this. And it's a little bit of a moral lesson that much of what you read about in archaeoastronomy is out, well, wrong, kind of blatantly wrong. Okay, but the point is that sun watchers are everywhere. And if you start looking around the Tucson area, just in the local area around us, you can find all sorts of things. For example, about a block or two that way is a statue of Father Kino. And he has two hands. One of the hands is doing something holy. In the other hand, he's holding an astrolabe. Back in the day, the astrolabe was the thing that you'd use for looking at the sun, for telling time, for telling direction, for getting latitude, for finding directions, for finding your paths. Hey, Father Kino was a sun watcher. And here we have sundials that are close by. And here we have, well, TAAA doing a daytime public star party. And we can see this from the campus here. And actually about 1 mile north of us, in the house that Martha and I moved into randomly, we didn't know it, there's a depiction of Kepler's law in the cement out in the back. And the house was intentionally constructed such that you have overhangs and such, so that on the first day of spring is the first day, the equinox is the first day on which the light goes into the main room. That was done intentionally. It was just a random house that we bought. There's sun watchers all over the place. And if you start looking around the American Southwest, you can start finding sun watchers all over the place. This is going back to pre-modern times. Oh, typically you have, typically throughout the whole area, you have sunrise calendars, where depending on where the sun rises against a modeled mountainous background, you can determine what the date is. You have to know exactly where to stand, but there you go. So every culture or every village had a place to stand, and they many of them had clans specifically designed to watch the sun and determine the dates of upcoming celebrations and things like that. And planting. You have these great northern roads, which are straight to remarkable accuracy. And that can only have been done astronomically and probably by the sun. There's heavy directional symbolism all around the place. So Navajo Hogans and Kivas with their supapus have very heavy cosmology with cardinal orientation. And the orientation of all these things, again, you really kind of have to do with the sun. Another thing that you have here, probably the second most famous petroglyph, is the crab supernova petroglyph here. Ah, right, remember that? How many people have you heard that, the crab supernova petroglyph? Yeah, it's in the majority of our intro astro textbooks. You know, but that's the one claim, or one of many claims actually, that is wrong. The guy who presented this claim, that is the crab supernova, and that's the moon on the morning of July 5th, 1054. That claim was presented at a conference by Jack Brandt in Mexico City. And the very next speaker gave the surefire refutation. Holy cow, you can even find it in the conference proceeding. It's back to back, claim, refutation. And this again is kind of showing you that, you know, it's in the majority of our intro astro textbooks, and it's wrong, known wrong. And it's kind of horrifying. But you know what it actually is, and we know this on very good grounds. What this is marking is not a crab and a supernova, it's marking a sun watching station. This is just more evidence that you have of sun watchers in the American Southwest. Now, if you start looking closer at the area around Tucson, you got to go looking at the Hohokam. Now, the Hohokam were, well, the modern name for a culture that appeared in the American Southwest, roughly central and southern Arizona, kind of centered on Phoenix and Tucson. And they have, whoops, excuse me. Okay, I jumped ahead one more slide. Let me come back and tell you about another sun watching situation here in the American Southwest. And that's going to be for the most famous of all the petroglyphs, maybe in the world, something like that. It's the sun dagger here. The sun dagger appears in Chaco Canyon up near Four Corners, and it appears on an isolated butte where nothing grows. And it's off in the corner right over here. And there are 3 slabs, naturally fallen rock. And behind those slabs is a spiral petroglyph. It's a nice spiral. It's actually one of the better ones. And Anna Schaefer found that on around noon on the June solstice, that you saw this weird dagger that just strikes through the heart, strikes at the center of the petroglyph, of the spiral. She thought that was significant, and she immediately went public with it, and the press and the public ate it up, and it became a great firestorm, and there you go. You know, but all through this, the archaeoastronomy community was kind of going, oh gosh, not again. There are a couple troubles with this claim of this sun dagger at Fajada Butte. One trouble with this is that the whole idea of a sun dagger has 0 ethnographic support, or actually 0, at the time, no archaeological support. Okay. Another big trouble is, hey, come on. There are petroglyphs and spirals all throughout the American Southwest. And there are an awful lot of shadows, and some of them are wedge-shaped, and they're always moving across the rock faces. And sooner or later, you're going to get a wedge shape that crosses over the center of a spiral. It's inevitable. So how can we know that this is intentional on the part of the Chaco Canyon people, as opposed to just being a random false alarm coincidence? Okay. And so for a long time, or for quite a while after the original report of this, it was big in the press, big in the public. But the real people were kind of, oh, I don't know, I haven't seen no proof. And that all changed. Let's see. There we go. That all changed when we started. Well, it changed for most people at a conference in 1996 in Santa Fe, the big Oxford conference. 3 different groups had gone out and done large-scale surveys looking for sun daggers, and they found them. They found them in large numbers. And all of a sudden, if you start finding a lot of these sun daggers that all work in the same way, the chance alignment argument gets to be a lot harder to use. And one of the groups, the Prestons from JPL, went off and did the following. They went off and for each one of their spiral petroglyphs that had a wedge-shaped thing to it, they could look from where the, well, from the petroglyph, they could look through the notch and determine where the sun had to be in the sky in order to create this. They could calculate the declination of it. And so they had a variety of indicated declinations for their 100 or so petroglyphs, okay? And here's the histogram of it. And this kind of knocks, well, my socks off, or did at the time anyway. What you see is you have a large number of these sun daggers pointing at a declination of -23 or so, within about 2 degrees of it, and a declination of +23. And you had a lot of them around the equinox, declination of 0. And to have this many over that narrow of a range, that's just far beyond coincidence. You can't get that. That is the proof that most of those sun daggers are intentional. Well, what about these ones down here? Well, that's what is consistent with the random background. Those are the chance alignments. So what it's looking like from this is that the people around the American Southwest went off and were aiming their sun daggers at the winter solstice, at the summer solstice, and at least some of them at the equinox. Okay, that was the proof, and there you go. So we have it. You see, a trouble happened is that starting back, this is back in 1996, fine. And since 1996, kind of basically nothing has happened. Back in 1996, there was one full-up case study. That was for the original Hohokam Butte, fair enough. And all of these were never published. One of the big studies was by a Tucson guy, I think he might have been in the TAAA, John Fountain. But he died, and he never published his results. And I haven't been able to get a hold of his results, although trying around. If anyone knows how to get a hold of John Fountain's notes, give a yell. Halton Arp doesn't respond. So what you have here is, since 1996, there's been basically no further work. Well, you got to be careful. People will, on occasion, come out and present another photo like this, fair enough, and then give 1 or 2 sentences of description, and then leave it at that. Never talk anything more about it. So we're kind of left with, this is all we wrote since 1996. Okay, before going on, let me go back and mention a little bit about the local Indians around the area around Tucson. And now we go to the Hohokam. The Hohokam were in South and Central Arizona, and they have the usual baskets. They have a large number of petroglyphs. Here's a sun circle with rays coming out. There's another circle, and who knows what that is? Maybe it's a flower. Maybe it's from Wanda. Who knows what? And the Hohokam lived, or their culture, defined by the archaeologists, is from, give or take 300 to 1450 BC. And their descendants are probably members of various Hohokam branches. And they're basically sedentary farmers, and they had all the usual crops. And they actually had a rather extensive irrigation system, especially up around Phoenix. And so they were very good at living in a very arid environment as farmers. We know about Hohokam astronomy. It's all rather simple, but it's practical, and it's very similar to the astronomy practiced by most other pre-modern societies. So they had ordinary garden variety, run-of-the-mill. Everyone had the type of astronomy which they had. Okay, so the Hohokam are people in the American Southwest about a millennium ago, and they left an awful lot of petroglyphs flying around in the area. Okay. Well, one of the petroglyphs that was found by John Fountain was this one. It's at Picture Rocks, and it was realized to be a sun dagger, much like claimed for Hohokam Butte. And just to put yourself into place, well, it's over near the end of Ina Road, Fair enough. And here's a picture. It's a small hill, and the spiral is on a flat rock surface, which is looking off towards the west. Here's a close-up picture of it, fair enough. And you can see this rock panel. There are all sorts of animals here. There are about a dozen animals. And here you can see people look like they're dancing and holding hands as they're dancing around. What's relevant for us right now is there's a nice good spiral here. When you actually go up and look at the thing, it's not very visible. It doesn't look like much. So this is probably not intended for public spectacle. Okay, fair enough. And claimed 3 times a year at the solstices and equinoxes, you get a little wedge of light, which then goes up and touches the center, is the claim. So the claim is that this is a working sun dagger. Now, with the realization that there really hasn't been much in the way of case studies, only the Hohokam Butte has had a case study. Jim Stamm, Jim is right there, Jim and I decided we should go off and do a full-up case study of it. So Jim and I are full equal partners on this game. Let me give a little bit of an introduction for Jim here. A little bit of a prelude. The TAAA is really one of the best astronomical societies in the world. And TAAA has many people who are world-class amateurs. Now, Jim happens to be a world-class amateur twice over. The first one is for all his work on occultation studies. And so the IOTA even came out and gave their, 4 years ago, 5 years ago, came out and gave their big Laird Award for lifetime achievement to Jim. And this is one of these big international things. So he's world-class in occultation studies. He's also world-class as the world's best observer of thin lunar crescents, one of these things that has had a large amateur community working long and hard. Actually, a number of people around Tucson also, back in the old days especially. So I first started getting data from Jim in the 1980s, something like that. And so I've been getting regular reports month by month of thin crescent moon visibility sightings. And Jim is by far and away the best of these in the whole world. And he's certainly has the longest. And he's one I actually believe, because the trouble is various others, they're going by different criteria. Jim is actually someone like us who's actually going off and reporting what he sees and knows how to look. So Jim is now one of the, I guess, the premier observer of lunar crescent visibility in the world, and he gets invited off to conferences in Dubai, expenses paid, and things like that. So he's world-class at lunar crescent visibility. And so he's world-class at 2 things now, 2 areas of amateur astronomy, and there we go. So I feel very lucky to actually have him going, because a lot of what we're going to talk about here for the sun daggers, he made possible here. Okay, so our idea is that we would go off and do a full case study of the picture rock sun daggers. Fine. And that entailed going out many, many times over, all times of the day and night, and taking a look and see how things are going. So on one of these times for the summer solstice, Martha, my wife, went out and took a picture, a moving picture, and through various work here, fine. This is a movie of the sun dagger, which appeared on APOD for August 5th, 2020. It's my 4th APOD, but it shows the sun dagger coming in here. Here you can see the wedge of light. Here's the spiral, and the wedge of light is going up and it's touching the center. There you go. So right there, we see that the picture rock sun dagger is a working sun dagger. By going out many times over, we can define how long, well, for about, this whole thing works for about a month. And for this, we find that this is the summer solstice one, and the one, this is caused by a notch in the rocks just above it. And when you look at that notch in the rocks, you find that the notch has been cut out by hand. The Hohokam went off and created this particular sun dagger. And that immediately provides a proof of intention, even though we only have one sun dagger in this case study. So well, there's the sun dagger again, and well, there's the picture, fine. So we have a whole up and working case study for how this actually operates. Let me briefly go through a number of our conclusions. First off, the sun dagger works for almost a month around the time of the solstice. And as such, this cannot be used for any calendrical purposes or any research purposes or any timekeeping purposes. Well, the only thing left is it's got to be symbolic. And we know that the Indians at the time, or more to the north, used these sorts of things for sun-watching stations with full symbolism. So we even have anthropologists who've gone off with local shaman to sites like this, where they would put feathers around and sprinkle corn, ground corn around and things like that. So and do this on the solstice. So we kind of know what's going on here. It's meant for a local ritual purposes. Now, exactly how the Hohokam were doing it, well, we don't know that, but it's certainly not any astronomical or any calendric purpose, because there's no accuracy in this thing. Another thing is that we can show that the sun dagger has to be intentional. If there was no intention on the part of the original Hohokam petroglyph maker, then it would be a meaningless exercise here. But someone went and cut that notch in the rock above to create the sun dagger. The thing is intentional. We aren't looking at random happenstance here. This particular sun dagger and the Fajada Butte and many others work by having a shape, a simple triangular wedge that happens to touch the center. And I thought I could give you a brief example of how this might work. Here I have our simulacrum of a spiral petroglyph. And here I have a wedge, fair enough. And as the sun moves around, you can see the wedge move around and cover the center and keep on going, okay? So that's what we're looking for, is we're looking for things like that. And that's what we saw in that movie of the spiral petroglyph painted rocks. Okay, but we get down to another level here, and we can start looking at the claims that the paint rocks sun dagger was used for the moon, for the winter solstice, and a variety of other rather even worse things. These claims are definitely wrong. They just don't work. For example, there is no sun dagger at the time of the winter solstice. And if you look at the moon, you go out in the middle of the night, even in full moonlight, you can't see the rather faded spiral, even from up close. You can't see it. It's just not visible. And to make a notch, the moonlight would have to come at a very slanty angle in this particular case. And so that makes, even with the full moonlight, you can't even see the wedge that gets formed. So they just don't work. And again, this goes back to the mantra, most of what you read about archaeoastronomy is just laughably wrong. And so here, this is wrong. Although you got to keep in mind that some of this was correct. Yeah, this does appear to be an intentional sun dagger. There's a bit of a balance you have to keep here. Most of what you read about archaeoastronomy is wrong, but there's good stuff out there still floating around. Another thing that we tried was we tried going off and seeing about making our own. Turns out it's easy, real easy. To find a place to build, to make a petroglyph, what you do is on the day you want to commemorate or mark, you just wander on over to a cliff face and you look around. And every cliff face or rock jumble has triangular wedge-shaped shadows, some of which are falling on flat surfaces. All you do is note them on the day you're interested in, and then it's easy. You just say, oh, there, draw a petroglyph there, and you say, okay, that's where it is. Okay, so we put it here. And then you peck out your petroglyph, and you can peck out these petroglyphs, in about a day, give or take. Depends a little bit on how good and how deep you're trying to do it. So the whole petroglyph making thing, the whole sun dagger making thing, from start to finish, could be done in about a day by an average person with no special knowledge. So the idea here that these sun daggers, Robert Redford goes out and makes deep documentaries about Fajada Butte. Well, sun daggers don't need no geniuses. It doesn't even take much work. You just do it. So that's a little bit of a myth that we can dispel once you actually start trying to do it. Okay, so this is the results of our case study, and it's been published already in the Journal of Astronomy, History, and Heritage. Fair enough. Well, after doing that, things were going swimmingly, and so we started looking around. There's an obvious thing to try. There is only, 4 miles away from the paint rock, there is a hilltop in Saguaro National Monument, the west version of it, where it's a small hilltop. There are other higher hilltops. It's a jumble of rock. And in that jumble of rock, in an area about the size of this room, there are 35 spirals. And there are about 30 circles, typically sunbursts or circles with a dot in it, or various versions of circles. And holy cow, all of a sudden, at one site, we can go off and do a good statistical study. And we have a big advantage here. Instead of taking people from many disparate cultures and many different eras and epochs all across the American Southwest, which is what the earlier studies have done, we can have the provenance of all our, from one small location, one community, one or at least a few lifetimes over. So all of a sudden, we don't have to say, well, maybe they did it this way and they did it this way. No, we have one provenance for it. And we have 35 circles all in one place, conveniently located for Tucson. So Jim and I have gone off and we decided to do a full-up statistical study of this. So this is called Signal Hill. It's over on the western side of the Saguaro West National Park, fair enough. And here's just some examples of, where's the pointer? Oh, here it is. Here's some examples of the petroglyphs you see there. The most famous and the most prominent one is this beautiful spiral, 8 levels deep, which is kind of pointing a little bit towards the North Pole almost. But the place is just chock full of petroglyphs all over the place. And so here are various examples. Here's a spiral going into who knows what that is. Here's a square spiral. Here's a spiral what looks more like a Trivia Pursuit set. Here's a spiral with a snake head. They're all over the place, okay? We got a lot of spirals. And so you can start doing statistics and we can start looking at things for real. We get a large number of things. We see what happened, what's going on in the mind of these villagers that lived close by. Okay, that's the idea here, is we have a lot of these things and we're going to do a statistical study to see how they were actually used and operated. So our statistical study has a variety of steps to it. First off, we had to go off and make a complete census of all the circles and the spirals. Now, I've been talking mainly about spirals as being centers, but the earlier claims, like the ones from that one big conference in 1995, point to circles also being used. So instead of a sun dagger could be pointing not to a spiral, but it could also be pointing to a circle. So we looked through the circles, and the first task was to go off and make a complete census of all the spirals and the circles. Next, we had to go off and find all possible notches on the horizon. And the way to do that, we didn't have to touch anything. One way, we did it actually a couple different ways, but the easiest to see way is you take a little hand mirror and you hold it up to near the surface and you scan around the horizon looking for a notch. And here, for example, I can now see, the notch here that I was using to create the sun dagger earlier. So we go off and we make a complete list of all the possible notches, which might actually have been used for a sun dagger. Fair enough. Okay, the next step is go off and use a homemade theodolite and clinometer to measure the altitude and the azimuth. Well, in this particular case here, you would be looking at the azimuth, the east-west line between, well, between here and the center of the spiral, and there will be some altitude above here that which you'd look in, fine, and you can measure that. And well, how do you measure it? Well, we didn't have a good answer. People in the past had gone off and used a Brunton compass, and thinking they were all fancy and hunky-dory. But it turns out that couldn't work for us because the rock in the area was magnetic. And so, well, you can't go and use compasses. So Jim went off and designed and built a clinometer where you can sight down here and you can read off the altitude of the sight line. So for example, in this one, I would sight down here, align them up, there we go. And then actually Jim was the one who was doing the sighting, and then I would do the reading off of the altitude. So we'd get an altitude, and then he would go off and use a theodolite, a homemade construction. Here's an example of it. And you could then go measuring, well, actually you'd do it through here. You could then go measuring, move it around and measure the azimuth of the line of the sight going through. And to calibrate the azimuths, we would go off and calibrate it by looking at various known mountain peaks. The Kit Peak domes were always a good one where we knew actually where we were looking at. And so we could get the altitude and azimuth of all of the various possible sight lines that we have here. Fine. Next, we have to go and take those altitude and azimuths and go calculating declinations, okay? So we calculated an indicated declination, and then that would then give us a date on which the putative possible sun daggers would work. And we all went and got ground truth, real ground truth, not just relying on our calculations, which is what people have done in the past. So we actually required that we actually see the real sun dagger going. Most of the time, our calculations were pretty good. Occasionally, something would come up and make it show us why we had to go off and get the ground truth of the thing. Fine. So we went and got ground truth by watching the sunbeams created on the petroglyphs. So we actually know, we can prove what the shape of the wedge of light is and so on. Another thing we did, which sets us apart from everyone else, is we went and repeated all the earlier steps for a series of ghost spirals and ghost circles. We needed a control study. So what we'd do is we would have a spiral. We did this for all of the spirals in our sample, and we selected a nearby spot of similar altitude, similar orientation, and so on. And we would, in our own minds, create a sun dagger centered there, and then would repeat all our analysis for that thing. So this would go telling us what the background rate is of sun daggers, just being created randomly. And so if the daggers we're finding are real and intentional, then the rate at which we find working sun daggers for the real petroglyphs is going to be much larger than for, well, these ghost sun daggers, okay? So we went off and did the whole thing again for ghost spirals and ghost circles. The next thing is to go off and start calculating false alarm rates. And what we found was that we actually had quite a large number or the number of real sun daggers was greatly larger than the number of ghost sun daggers. So that shows that there's something real and intentional going on the signal hill. Okay, so here's the numbers. I shouldn't go over this too long. We can go comparing the number of sun daggers for the ghosts versus the work for the real events. And there is a large excess for the real things as opposed to the ghosts. This is our background rate. And the difference here is there are roughly 10 working sun daggers. Another way of looking at it, just looking at equinoctial and solstitial ones, we have 6 working sun daggers. So the number is somewhere between there, 6 to 10 working sun daggers. And if you start looking at how they're shaped, it turns out that the working sun daggers are all triangular and a relatively small opening angle, whereas the random ones are just all over the place. So we're getting at the intention of what the original makers did. They were looking for something kind of triangular of a relatively small opening wedge angle. And we also found that they all are going off and touching the center of the glyph. So it's the center that is mattering here. So what we have is basically this is a proof that the Hohokam that were going off and making all these sun daggers on Signal Hill were doing it intentionally. We're getting an idea of what their intention was. They were making it so that it interacted with the center, and it was circles and spirals, and the wedges are triangular shaped with relatively narrow opening angles. So we're doing a statistical proof of the intention of what these Hohokam were actually trying to do. And it turns out there are 7 sun daggers which look good, significantly above average. Here are the pictures of them all. And you can see, well, here's the big famous one, nice good triangle. Here's a thin wedge. Here's a starburst with a triangle there, and so on and so on. So these are the 7 working sun daggers that were clearly intentional on the part of the Hohokam. Okay? So we're actually getting into the minds of the people way back when as they built these things. And so we have these 7 intentional sun daggers that are all pointing to the solstices. And we have a variety of conclusions. Many of them we've already mentioned. They were intentionally made because we have a statistical excess here that you can't account for by random chance. They were aligned to work on the solstices and the equinoxes. Okay. For cultures the world over, solstices and equinoxes have always been important dates, and that's when they're working for. It's not like they're working on St. Patrick's Day, which some people do them. And what they always work is a simple wedge shape of light touching the center of spirals. Okay, so we're getting at some of their motivation of what they were aiming for here. And however, we also have many spirals that have no possible shadows, no possible relationship to spiral, or to sun dagger, sun anythings. And so there has to be something else going on with these spirals on Signal Hill. You have some spirals, a significant number, have to be astronomically intentional. But that leaves the others as no possibility of astronomical use. So we kind of are scratching our heads. We don't have a good answer to this, by the way. There apparently are, well, you could call them 2 classes of sun daggers. One class, which is intentionally astronomical alignment for the solstices or equinoxes, and the other, well, I don't know, maybe they're advertisements Wanda slept here. You know, I don't know. You just don't know. So we haven't solved everything, but there you go. Another thing is that sun daggers are really easy to construct and to build. You can do it in a day without even thinking, and it doesn't take any special knowledge. This is just ordinary folk going off doing ordinary things, no big deal. And you do it all throughout the American Southwest. It's not even a one tribe sort of situation. So clearly the sun daggers are some sort of a sun marker for ritual purposes. Probably probably much like the Hohokam Butte sorts of things. Okay, so there you have it. That's our conclusions on sun daggers. And this is all done by simply, hey, Jim and I going out with homemade instrumentation. Oh, that's right. I didn't show you, did I? We also, or did I? Where is it? You have a a measuring engine here. You also have that, you can get the altitude here. So Jim also made this. But the point is that you can find out what these things are, and it's kind of neat going back and being able to understand what's in the minds of these people who lived 1,000 years ago simply by looking at the statistics of where they're at. Well, watching the sun has a long, varied tradition throughout the world. Basically, all old cultures are sun watchers in one version or another, because it's your primary tool up in the sky. So, for example, you have Ptolemy went off and made a bronze ring, which he could go measuring altitudes of things with. Hey, Thomas O'Keefe, I don't know what that got brought up for. You also have Eratosthenes going off and measuring the radius of the Earth using shadows of the sun. And in Jaipur, India, you have people doing a wide variety of astronomy research. Here's one. And these are all for people looking at the sun when it's on the meridian, the north-south line. It's the highest point. So here's one. Off in Bologna, there was a meridian line by Cassini. Actually, there are a large number of these, but Cassini was the one that had the most famous of them. And what he did was he put a hole high up in the wall of the cathedral in Bologna, and it went down and cast over a very long stretch a sun image. Here's a picture of the sun, and here this happened to be taken at the time of local noon during a partial solar eclipse. So you can see that you get a large image of the sun. This is just ordinary pinhole camera projection, nothing more than that. And of course, as the day goes on, the sun image goes across that way, or I guess actually, yeah, it would go across that way. And so here's this big long line, and you can go positioning the sun along this line to give you the dates and do a variety of things like that. Okay, fair enough. So there's a long history of looking for the sun on the meridian. Fair enough. And hey, I do an awful lot of practical re-demonstrations of old historical phenomena. So I got to start thinking, why not go off and kind of make your own one of these solar transit instruments? Okay, fair enough. And so, hey, clearly when I was looking at this, this is my study. Here's my computer just down here, looking out at my, well, there's a wall here and a nice saguaro there, there are the Catalinas. And so I decided to go off and build something much like what you saw in the Christian cathedral in Bologna. Well, clearly it's on a different scale. So what I did was on the wall, this is a good north-south wall just outside my study window, I placed a horizontal meter stick and just a rod sticking out of the wall, okay? There's a gnomon. And so here's a little bit more of a close-up view. In this picture, the sun hasn't quite yet illuminated the west side of this wall. And there's the meter stick, and there's the rod sticking out. And in this case, you can see that this rod is casting a shadow right there, and you can go off and measure that shadow. Turns out I measure it from inside here. I just hold up my binoculars and read off the ruler. There you go. And you do that day after day, and you get a measure of the position of the shadow in this instrument, which you can then turn into the altitude of the sun, for example. You can also go getting the time of things a little bit later. Here's a little bit of a different view looking down. And here's the gnomon, just a rod. The ball at the end is just simply so people don't go accidentally sticking themselves with it. Here's the ruler. You can see the shadow of this on the ruler, and you read off the ruler, read off the shadow position right there. Okay. So you can go off and you can go making one of these a meridian transit instrument actually fairly easily. I don't think anyone's actually done this since the 1600s, where they've actually gone off and started making measurements of it. And this is something, so I started going off and building this, partly to try and get some idea of what ground truth is, what is possible, what's not possible, see what you can do, see how accurate you can get. Okay, so I built my own meridian transit, and the cost of the materials was $10, something like that. Took about an hour to build. We aren't talking expensive NSF material here. Okay, so by measuring the position of that shadow on the ruler stick, I know the geometries of it. I can then go calculating the altitude of the noonday sun. There you go. Only mad dogs and what was that? Englishmen go out in the noonday sun. Well, this is the noonday sun. I never went outside because I was always looking from inside on this. And you can go using the position on the ruler and the known geometry. You can determine what the altitude of the sun is at noon every day. And when you do that, here's the plot showing all the observation. This is about almost 2 years of observations, and I have 321 noontime altitudes. And you can see, the sun is the zenith distance is about 10 degrees. So the sun is, this is midsummer, midwinter, and so on, okay? And you see a nice, good, nearly sine wave. It's not a perfect sine wave, it's pretty close. And you can spot when summer is, when this is highest up, and so on, fair enough. And from just making these timings, not even timings, just by looking at the position of the shadow from day to day, you can go getting this curve. And from this curve, you can get quite a wide variety of things that were especially of interest to old-time astronomers. Nowadays, hey, we know it all. But I'm trying to see what could be done for old-time astronomers. So one of the things you get is you can find out how far north the sun goes, how far south the sun goes and how far north the sun goes. And the difference from the center line is going to be the obliquity. And the obliquity, you might recall, is how tilted the Earth's globe is with respect to its orbital plane. So you might recall that globes are always not with the North Pole up, but with the North Pole tilted a little bit. Well, that's what we're seeing in here. And so you can work backward from this, from this plot, and you can work out how tilted the Earth happens to be and play games like that, okay? You can also determine what your latitude is. The latitude altitude is going to be halfway between here. And so I have a good measure of the latitude of my front yard. Well, it's accurate to about 2 miles, okay? Not bad. Not bad just for looking at a ruler every day. There you go. You can also determine how tilted the Earth's orbit is, the obliquity. And so the obliquity is 23.48 degrees, which is pretty close to the value we know it is from elsewhere. But the point is I'm doing this all on my own without reference to anything here. And you can also determine when the solstices are, and you can determine when the equinoxes are, and so on. And so from that, you can determine how long each season lasts. So for example, winter lasts 89 plus days, whereas summer lasts 93 plus days. There's a 4-day difference, okay? Now, the ancient Greeks knew about this because they were doing largely similar sorts of things way back when. And the troubles in here caused a substantial trouble because the early Greeks had the ideal that everything was moving in perfectly uniform, perfectly circles. And if that happens, you can't have the seasons having different lengths. And so this is what forced them into having, or having many of their epicycles in their model. They had to explain this data. Okay, fair enough. And so, we're recovering this in here. So summer lasts about 4 days longer than does winter. In modern day, we know, this is simply because the Earth has an elliptical orbit and it happens to go a little bit slower around the sun around the time of summer. Okay, we understand that. Now, back then they didn't. They had epicycles on epicycles and things like that. We actually can go off and make real measurements of this. So here we have a variety of things of defining the geometry of our solar system just by looking out of a window at a ruler and a rod. Okay, fair enough. There's another way you can do it. You can actually take this telescope and you can point it off to the sun, fair enough. And then you can go reading off the declination on the setting circle. And you always do it around the time of around the time of midday passage. And so then you don't even need an accurate polar alignment. You just simply are looking at the north-south motion in here, okay? And when you do that, I can then go read off of the setting circle. I can go reading off what the declination of the sun is. You have to be careful to normalize everything. It turns out the way I have things set up, the offset is basically 0. But what you have here is you have a simple device for going off and measuring the declination of the sun as a function of time, okay? Which is basically the same thing I was doing with that ruler and knob arrangement. So you come up with data here, and I've done this from March of 1 until, actually, yes, actually, I don't think we did one today, although it's not included in this graph. And so you could go getting the sun's declination as a function of time of year. And from this, you can go calculating, well, you can go calculating the obliquity of the ecliptic and the lengths of the seasons and things like that. It turns out that with this method, the uncertainties, even with the relatively fewer observations, the uncertainties are substantially larger than my very simple ruler and rod measurement. So, I've done all these same things with the telescope and using the setting circles on here, but the uncertainty is about 10 to 30 times less accurate. So I'm going to now start ignoring those. And those are not included in what you're going to go getting. Okay. Now at this point, we start hearing about the Analema program, which our astronomical league, I guess you're the coordinator, has come up. Doug Smith was telling us about this Analema thing, and I was putting two and two together saying, hey, gee, I can do this. And so I started going off and doing it. What the Analema is, it's a measure of where the sun is in the sky at noon. Here you have the sun's declination. So the sun goes between, well, January, it's far south, the summer, it's far to the north. And the sun lags or is ahead of a clock. And it creates this classic analemma shape. And you can see these analemma shapes on most globes now. Well, there you go. Okay. Okay. So it turns out the Astronomical League has just started, or 2 years ago, something like that, has started an analemma observing program. And oh, it has? Well, there you go. Okay. The analemma program's been around for 15 years. There you go. But the realization is that what I had been doing was basically the same sort of observations that would be needed for the analemma program. So I started doing the analemma program. And what this analemma is, you've all seen it, even if you haven't quite realized. It's that figure 8 shape thing, and you can see them on globes, okay? There we go. And so what happens is, as the year goes on, the sun moves north and south, and because the Earth has an elliptical orbit, the Earth speeds up and slows down variously, creating the Earth going ahead or behind and creating this figure 8. Okay. So this is the analemma observing program. And so my realization was that, hey, what the heck? I can start doing this here. Fair enough. Okay. And using the observations that I have. So how to do this? Well, you can go off and take this. You can go take this. Well, I've already have the altitude of the sun by measuring the position on the ruler. That gives you the altitude and the declination of this half of the analemma. The other part comes in because on this same wall, what I do is, well, this is just before noon, and the wall is basically in shadow. Well, here's a little bit of brick sticking out, which has just caught the first light of the sun. But what happens here is as the sun moves around in the sky, it starts illuminating this side of the wall. And so I defined a part of the wall over here where I can spot the very first ray of sunlight hitting it. In this picture, the first light particular knob happened at 12:29 and 20 seconds afternoon. And for redundancy, I went off and defined a second place. Actually, it's just a crack just a little bit above it, which happens about a minute and a half later that gets illuminated. So I'm doing 2 timings, and then I'm taking the average of the 2, trying to beat down the errors a little bit. Okay, so by timing, well, this is basically local noon, because this is a good north-south wall, and I'm timing when the sun is just starting to illuminate the west side of the wall. And so that is effectively the time of local noon. So I'm measuring the time of local noon, and the sun speeds up and slows down because it's an elliptical orbit. And so that time will vary. That's what the analemma is designed to show. Fair enough. So my activity consists of every clear day, or at least many of the clear days, just sitting at my desk, looking out, and then observing when that particular knob happens to get the first light on it, and when that particular edge happens to get its first light on it. And then I average the 2, and that's my time of local noon. Fair enough. And then I can go plotting those up here. This is the average meridian crossing time. And this is done from March 2020 until actually today. I got a good observation today. So this is going to be 361 measures now. But you can see that the time of local noon goes up and down in this very characteristic thing. This is called the equation of time. Fair enough, and it's well known. But you can go off and measure it on your own. Fair enough. And this is caused by actually 2 separate effects. One effect is caused by the sun moving north and south, which turns out it makes things move a little bit slower across the sky. And the second effect is due to the eccentricity of the Earth's orbit. We know that the Earth's orbit is out of round, and when it's relatively far from the sun moves, well, Earth actually is moving. The Earth moves a little bit slower, and there we go. Okay. So here is my measured equation of time. Okay, there we go. And you can break this down into 2 sine waves. You have 2 sine waves, one of which, the green line is for the eccentricity, the out of roundness of the Earth's orbit around our sun. So you can actually go measuring what that eccentricity is from this, okay? And then you have the yellow curve, which is caused by the obliquity. As the sun moves further to the north, it appears to go slower. On the equator, it appears to move fastest, and so on. And so the observed equation of time is the sum between the between the green and the yellow, and those 2 is the blue line here, and the red observations in the back are the actual observations. So I can go breaking down my observed light curve, or not light curve, my equation of time curve. I can go breaking that down, and I can go calculating from my observations what the obliquity of the ecliptic is. There we go, with pretty good accuracy. And I can determine when the solstices and the equinoxes are, fair enough. And I can go determining what the eccentricity of the Earth's orbit is, how out of round it is. Turns out the Earth's orbit is not much out of round, but it is out of round, and I can go measuring it with pretty good accuracy. And I can also go measuring when the Earth is closest to the sun, the date you would call it the day of perihelion. So just by looking out my window at this wall with very simple equipment, I can start determining a lot of the properties of the Earth's orbit here. And so I can go off and go creating my own analemma, and here it is. So this analemma figure, it's that figure, very much like on globes where you always have these figure 8s that no one ever really understood what they meant. Well, you can go making your own. So here is my analemma, which shows the equation time, which is how much the sun is lagging ahead or behind the average smooth going sun. And here you have the sun's declination, and it creates this figure 8, this very characteristic figure 8. It's the same one that's shown here on the globe, okay? And I can go annotating it by showing when the fall equinox is, when the spring equinox is. Those are the times when the declination is 0. And you can also see when the summer solstice is and the winter solstice is. And the angle from here to here and from there to there is going to be the obliquity. It's how tilted the Earth's orbit is. And you can also go measuring when the perihelion and the aphelion is. Now, this figure here is one of the ones required by Doug for the Analemma observing program. So I have put together all of the observations, probably don't want to read all this. So I put together my report on the Analemma observing, and I offer this to our Astronomical League correspondent, who also happens to be the guy who runs the Analemma program. And that is my submission, hoping to get the Analemma award. We'll see how that goes. Anyway, so one can go a lot further past this. And here's a way of doing it. It's actually a way I started back when I was in 7th grade, of all things. I just got, well, actually with this telescope, I was observing the sun. I was playing games of trying to determine fields of view, and I was looking at how large things were, and I was letting this, this doesn't have a clock drive, so I was letting the sun drift, and I started timing the drift time of the sun. And one thing led to another. I started realizing you could measure the angular diameter of the sun. So I started back in 7th grade an observing program where I would go off, and on various days, I would go measuring the angular diameter of the sun by simply timing how long it would take. I would go centering up the sun here and so on. And I would then get my, well, back in 7th grade, it was my wristwatch with a sweep second hand. And I would look, and I would first center the sun in the field of view so that when the sun starts leaving, because I didn't have a clock drive, we knew that it would be going along a radius. And so I would then start my watch, or start timing. I'd note the time when there was internal tangency here. Then I'd wait a little bit more than 2 minutes until the very last gleam of the sun disappeared. And that time is going to be proportional to the angular size of the sun. So when the sun is at perihelion, when the sun is relatively close, you have, well, the sun is relatively large, and it takes a bit longer time for the sun to disappear. When the sun is at aphelion, the sun is further away, and the sun is smaller, and so it takes smaller time for the sun to disappear. So I started making a large number of measurements of it here, and there's an awful lot of scatter. Hey, with a sweep second hand, I was just a kid. There you go. Conceptually, somewhere around in here, I ran into the trouble of realizing that the velocity of the sun when it's on the equator is fine, but when the sun goes further north, it will take longer to go across the eyepiece. Just simply because of the geometry. When, for example, imagine if you get up near the pole, it's going to take the sun forever to move its own diameter. Okay, so I realized you had to go correcting for that, and now I didn't know how. In modern days, I would say, oh, it's just you multiply or divide actually by the cosine of the declination. You know, back then I was just a kid. I wasn't even totally sure what declination was, much less any idea what trig was. So I came up, and this one I'm a little proud of. I came up with my own correction. What I did was I observed stars at various declinations. I observed how long it would take a star to pass through entirely the diameter of my field of view. And I'd time that. I'd do that for a wide variety of declinations. And so I had an empirical correction factor to go off and convert my observed time for the sun to completely go out of the field of view and convert that into an equivalent diameter if the sun were on the equator. And so that's what I'm plotting up here. And you can see the data is pretty cruddy, a big scatter in it. So whereas the time, well, the sun is relatively large. So this is winter time and this is summertime. But you can see that there's a definite effect going on in here. Now, back in 7th grade, actually be getting into 8th grade by the time we're up in here. In 8th grade, my analysis didn't go much further than taking an average here and an average here and working that backward into ratio -1, 3.4, well, 3.4%. So I didn't even know enough to convert that into an eccentricity. Well, with now knowledge, I would be able to convert the number to an eccentricity of that. Okay, fair enough. But back at the time, there was no precedent. I still have never seen anyone even trying anything like this. So this is my 7th grade project for measuring the eccentricity of the sun's orbit. Okay, fair enough. And that's the same sort of thing that you have that I was doing with that meridian transit thing on the wall outside my office. Okay. Well, back in 1970 to 1971, I went off and made 98 measurements of it. And in modern times, I've gone back and fitted a sine wave to it, and I can come up with a date of perihelion, which has a pretty large error bar, but it's correct. And I come up with an eccentricity from this data, which is actually pretty good. Okay. And then I stopped. Oh, I don't know whether I found girls then or probably actually found the local astronomy club, but there you go. Is Martha listening? Oh, Martha. Ooh, gotta be careful here. I picked it up again in 1986 when we were living at Goddard, and I made 40 measures, not well distributed, but it's enough to be able to determine the time of perihelion, and also enough to be able to determine what the eccentricity of the Earth's orbit is. Then I started picking it up and doing it again in the year 2020. Hey, this was just around the time when COVID started coming around. And so I was just looking around for things to do. And so here are my observations over the last 2 years. And what I was doing was I was being more careful, certainly, than I was here. Here I was just looking at a sweep second hand on a watch. Here I was using a little small pocket stopwatch, or wristwatch stopwatch. And here I was actually using the stopwatch function on my on my iPhone. Okay, fair enough. And I would start doing 4 different observations at a time. And that improves the accuracy by a factor of 2, and so on. So here's for my last year's observations. I actually define the size of the sun to pretty good accuracy. And you can see the X of the Earth having an elliptical orbit. Here, the sun is relatively large, and that means that it's relatively close. This is around the time of January, and this is June, when the sun is relatively far away, so the sun has a relatively small size to it. And you can go fitting to this, and I come up with a date for the perihelion of the sun, or well, actually of the Earth's orbit, and the perihelion comes out to be January 5th, with an error bar of 1.3 days, which fits well with what we know from modern work. And I also get an eccentricity of the sun, of the Earth's orbit around the sun. And so all of this just simply by going off and making some simple dumb timing measurements where you go and point this at the sun, fair enough, you do this, you center it up. You get the sun all centered, and you wait. When the sun first touches the edge, you start your stopwatch, and then you stop it at the end. Trivial. Anyone can do it. Okay, there you go. Now, here I am getting the eccentricity of the Earth's orbit and the date of perihelion and a variety of other things too. Well, okay. I have been able to determine the date of perihelion. Okay, well, the early measures back in the 1970s when I was, hey, just a kid, the error bars are relatively large. Okay, fair enough. And more recently, one can get the error much better. And so what you can do is you can start looking for a drift, the perihelion, the phase of this. This would be basically looking for the precession of perihelion. This is like precession, like what you would get from general relativity. Oh, yeah, right. At least some people should be smiling. What the gall of that guy. Yeah, right. And you'd be right, too. But what I have here is I have a measurement from 1970, a measure from 1986, and a measure from the last year of the position of the perihelion. So I can start looking for the advance of the perihelion. At this point, I got to be careful not to smile too much here because I'm being, if you haven't got it, being a little audacious, shall we say, and I will gloss over an embarrassing factoid here, but you'll catch it. So what I have here is a test of general relativity. General relativity predicts that an elliptical orbit around the sun should go rotating around. General relativistic effect. That means that the date of perihelion changes over time. And I've got measures of the date of perihelion. I can go off and test general relativity. At least some of you are laughing, which is good. Okay, anyway, so I have a measure of the precession rate, okay? And let's see, here it is. My measured precession rate is, well, negative whatever that means, 0.75 plus or minus 6.45. And that basically it's saying, to the best of my measure, the precession rate is 0 to within my rather large error bars, okay? And then one can go comparing this and saying this agrees with the general relativistic prediction. So yes, I have gone out and confirmed, I have confirmed general relativity. Or maybe a better, fairer way of saying it is, yes, my measurements are consistent with general relativity. And at least some of you people should be laughing. Yeah, you obviously are an astronomy student. There you go. Others of you should be laughing, but whatever. So I have my personal, a test of general relativity. And back at the university department where I came from, oh, there were about 20 general relativists around, and I would be flabbergasted if any of you told them that I came up with this, because they would look down upon me for even having thought to do this. Anyway, there you go. Okay, so let's go on and do another type of test that I can do with the data. And that is I can go off and test Kepler's laws. The first law states that the orbits around the sun are going to be elliptical in shape, with the sun at one of the focuses of the ellipse. And I can test that. Because after all, assuming the sun doesn't change in size, then the parent angular diameter of the sun, which is what I was measuring, will tell you the distance to the sun. Okay? And so I can go scaling everything to 1 astronomical unit. I can tell you the distance to the sun on these various states. And so here I have plotted all my red observations as you go around the orbit. And well, they actually match pretty well this black line in the back, which is a perfect circle. So this is all to say that my measurements show that the Earth's orbit around our sun is a pretty good circle. And indeed it is. However, this depiction doesn't well show what's going on here because everything is scaled out. So you notice that all of the measurements around in here are a little bit further out from a perfect circle. And in here, they're all a little bit inside of that perfect circle. Okay, so here's a better representation. So you have Kepler's law. Again, this is basically a test of Kepler's law. And so what you have here is, here I have the sun's distance, which is basically the inverse of my measured diameter of the sun. I'm measuring the diameter of the sun with my timings. And so I can invert it to go getting the distance in astronomical units. The reds are my observations. And if the sun happened to be, well, if the Earth happened to be going in a perfectly circular orbit around the sun, well, the distance, the Earth-sun distance would be constant, and you'd get a constant distance. That's clearly not the case. So instead, what I see is basically a sine wave, and that's exactly what you expect for an ellipse, okay? So you could look upon this as, hey, I've just gone off and proved one of Kepler's laws, that we're dealing with an ellipse. That's the shape of the Earth's orbit. Well, you got to be a little careful there because the shape of the Earth's orbit here, there are other models. For example, a simple offset circle when you're dealing with low eccentricities, a simple offset model is largely equivalent. Nevertheless, what I've come back and done is basically demonstrate the applicability of one of Kepler's laws. Well, there are two parts to Kepler's first law, and that is that the sun happens to be at one of the focuses. Fine. So you can go asking the question, well, gee, what would you expect if the sun was at the center of the ellipse as opposed to at one of the focuses of the ellipse? And well, you'd get this, and that disagrees totally with observation. Or if the sun is at the other focus of the ellipse, well, you get this, and that clearly is wrong. So what I'm finding is that my measured observations are in great agreement with Kepler's law. And there you go. Wow, I'm going off and proving Kepler's law. I'll be done here in 2-3 minutes. Anyway, for Kepler's second law, you can go off and ask about the speed of the orbit. And what you have is one possibility is a constant velocity throughout the orbit. Another one, Kepler's law, is you have these equal areas sweeping out equal times. And my observations here show if you take out the swept out area over one-day intervals, my observations are the red dots made larger, and the blue line is what you'd expect for Kepler's law. And this is what you have constant velocity. So I've just gone off and proved that the Earth is going around in orbit has a variable velocity, and that it agrees with what Kepler's law would have and have. Anyway, there are my collected results. And all of this is just done by visual observations of things around me. No big deal. And kind of amazing what you can do when you just look around. And so I've been able to prove some of the more important of the astronomical things. And there we go. So Kepler's law actually works. And you can go out and prove it in your front yard easily. So I'll stop there.
Okay, do we have Facebook questions? I
See if anybody has questions. Okay, from Zoom, let's see. Alex and Thomas O'Keefe kind of asked the same thing. Alex was asking, why are they spirals? Why not concentric circles when you're talking about those things? And Thomas says, why spirals? Why not an X or box or a picture of the sun? Why spirals all over the world? Did they talk to each other?
Not all over the world, all over the American Southwest, where there's cultural continuity. And I don't have a good answer for why they chose circles to depict their sun daggers. I wish I knew. Probably there was some, who knows what's it, the early Johnny Carson showed an example, and it spread to all the cultures in the area. I don't know. No good answer to that. But you don't find sun daggers in any other cultures outside the American Southwest. So it didn't spread far.
Okay, Bernie Stinger asked, does precession have any effect in the position of the daggers after 2,000 years?
No, because what the daggers are basically measuring is maximum north and the maximum south extent of the sun's motion, at least for the solstices. And that doesn't depend on precession. That would change the date on our calendar, but it doesn't change the actual indicated declination. And so it turns out that doesn't matter.
Okay, and last one on Zoom is from Saban. Did you correct the angular diameter measurements in seconds based on the sun's speed in its orbit? That makes sense? Did you correct the angular diameter measurements in seconds based on the sun's speed in its orbit?
Okay. I think I caught that. So what happens is I'm basically timing how long it takes the sun to cross, well, a circle, but an edge. And if the sun is relatively far north, the sun moves slower with respect to the background. And so you have to do have to correct for that. That was that trouble that got me early on in 8th grade. So yes, you do correct for that. We now know easy ways of doing it. You just multiply by the cosine of the declination. Okay. Back in 8th grade, all I could do was empirically try measuring something that I now know to be the cosine function. There you go.
Okay, questions for the in-person audience here? Anybody have questions? You can just raise your hand and I'll bring the mic to you.
Is there any significance to the number of rings in the spiral? You didn't identify any, huh?
The number of birthday presents the local shaman got on their 3 birthdays ago. No, we have not been able to work out anything like that. You get as many good intentional alignments with large spirals as with just a couple turn spirals. And hey, these are people 1,000 years ago in kind of an alienish culture, and we're lucky we pulled out that they were intending to have thin wedges pointing to the center of spirals and circles indicating solstices and equinoxes. We're lucky we got that far. And no, I don't know.
Okay, all right, there's a question in the back. It'll take me a minute to get there. Well, hopefully not a whole minute, but anyway, I'm making it. Here you go, Jim.
My question is, could they or did they make sun daggers for when to plant certain crops?
As far as we know, no, because the working sun daggers all point to either the solstice or the equinox. And that would be timed by their calendar, which will presumably have some relationship to when you plant crops. But I think you plant crops fairly far away from all the times that would be indicated. No, these are, the sun daggers are pointing to significant times on a solar calendar. And you might know, oh, we plant our maize crops 38 days after this sun dagger works. Or we don't know how they did it because we don't have any ethnographic evidence of the sun daggers.
Okay, other questions in the audience here? All right.
Thank you. Yeah, maybe this question is better for Jim Stamm, but I was just wondering, he's a thin crescent expert. What does he learn from studying the thin crescents and recording them and everything? And what can we as amateurs do to help with that?
You want to take it? Oh, okay. The question was, what can we learn from these thin times of the thin crescent? And kind of part of the answer is we can't learn too much, although we can learn about how old calendars would work. We can, the whole thing is into much of a game almost. People striving to catch the youngest crescent moon. Jim had a couple of records of those. I don't play that game, but he's good at it. So the utility of this for modern people is not much, unless you operate on a lunar calendar. If you're an Islamic person, the dates on which you go fasting for Ramadan are determined by when you locally can see the thin crescent moon. So the dates on which when you go fasting is determined by that. So it matters for them.
Okay, Jim Stamm, did you want to say anything else? Okay, we have another question.
I'm just going to say that I think a lot of this is oral tradition back then. So from my
What else could it be?
anthropology, that's why I think this part is very intriguing.
Yeah, because of these astronomical and technical aspects, we can get back into the minds of people 1,000 years ago that didn't have any writing, and none of their traditions really survive to today. Because it's a technical astronomical thing, we can actually understand what they were doing, maybe only in a fairly limited way, but we are getting some insight into what they were doing way back when. because many of these cultures don't have writing. And even the ones that do, usually pretty ambiguous.
The question was about, what about Chaco Canyon?
Yeah, so Chaco Canyon does have, well, the original sun dagger, and that no longer works anymore. Because what happened, enough visitors went up to the top of that mesa, that little rocky area, and the rocks slid down. So the Fajada Butte sun dagger doesn't work anymore. There we go.
Okay. Okay, thank you so much, Brad. We really appreciate this. And we're delighted that Jim Stamm could come tonight and his family came with him, and that's just really delightful. Thank you. We hope you'll come back. Okay, we have another presentation, but I think we need maybe a 5-minute break here. And so if we could take 5 minutes and come back quickly, then we could start with the next presentation and move along. Okay, our next presentation is Dr. Mary Turner, and she, as you know, is our master observer, and she's going to talk about her seasonal objects, our objects in the sky for the next quarter.
Okay, so here's the list of 10, but don't worry, we are a little late, so I won't go through all of them. We'll just give people enough time to count all the ballots that have been turned in. So standard, a little bit about a constellation, and then some of the objects in the sky. And this is good time to look at globular clusters, and I like looking at globular clusters. Mic on okay? Okay, I can't hear myself. Okay, so constellation I want to talk about, one I like to talk about is Hercules. There are many different representations of Hercules. And of course, we can all see how we got Hercules from this particular star grouping. As good as any. Okay, so some of the myth, legends, and lore associated with Hercules. We talk about the 12 labors of Hercules, or at least there have been movies about them. It was originally supposed to be 10, but you know, he did those, so you might as well make it more difficult. One of those you can win if, but there's more. So the labors basically take us through the celestial year, and this monitor is really hard to see. First one was to slay the Nemean lion and to bring back its fur. And basically this points to the constellation of Leo the lion. Also supposed to slay the Lernaean Hydra. You know, there was a lot of violence associated with the Hercules legend. So when the sun is in Cancer, Hydra is nearby, and the crab and the snake and all those fun animals, creatures are up in the sky. And then again, Hercules is supposed to kill something. And except the Ceredian hide, he was only supposed to capture that one. And this refers back to the constellation of Scorpius. He was also supposed to capture the that boar, wild pig. That's not quite a javelina, but in the same family. And of course, he was supposed to clean some very dirty stables within a single day. And this is to represent all of the sins being washed away. And he did this by diverting a river and just sweeping out all of the manure. Wish we could Well, it appears my formatting changed. Why would you want to kill birds? Birds are nice. But we all know that there were several constellations in the sky that represent different birds. So as we pass through the constellation, it's sort of acting like a calendar. Because as presentation we had earlier, which was absolutely fascinating, tough act to follow, this sky was the calendar to the ancients. He was supposed to steal the man-eating mares of Diomedes, and this references to the Aquarius and Pegasus constellations, obtain the girdle of Hippolyte. It's one piece of attire that I'm glad has disappeared from the face of the earth. Get some cows. The Milky Way refers to the cloudy appearance in the sky. Those of us who in particular go up to the Grand Canyon and other dark parts of Arizona can understand this milky concept of the Milky Way stars. Stealing apples from the Hesperides. Ursa Minor was the seven sisters of the Hesperides. Ursa Major was their apple tree. And then he was supposed to capture the dog Cerberus, and Pisces, that part of the sky, originally represented the underworld. So basically, again, as you go through the labors of Hercules, you're basically circumnavigating the sky around us. Other legends and lore was he was the son of Zeus. So he was a demigod. But you'll notice he was the son of Zeus and Alcmena, not the son of Zeus and Hera, was Zeus's actual wife. So Hera wasn't too thrilled about him and attempted to have him killed as an infant by having snakes eat him. I guess that gives him a good reason for wanting to kill a bunch of other animals. He also suffered from significant bouts of insanity, which is what led him to have to go through these 12 trials, because in one of his bouts of insanity, he killed his wife and children, and these labors were his penance for doing that. In between everything else, of course, we have seen other legends of Hercules. He did journey with Jason and the Argonauts. He helped the gods win the war with the giants. He helped pillage Troy. He killed Laomedon. And of course, he had his own TV series on television for many years. No. I used to travel to Hong Kong. And times like the first weekend, you just want to relax in the hotel. And they had an English language television channel. Xena, Hercules, Sinbad, followed by Xena, Hercules, Sinbad, followed by Xena, Hercules. Yeah, I loved a lot about Hong Kong. Television was not one of the things I enjoyed about Hong Kong. And of course, once he was, in the end, he was poisoned. He builds his own funeral pyre, climbs up on it and sets it afire. And then he gets carried off to the heavens in a chariot drawn by 4 horses, because again, since Zeus was his father, there were a lot of Zeus's illegitimate children represented up there in the sky. A little bit about the Hercules constellation. It is a rather large constellation in terms of the area. It's about the 5th largest. It is the home of a supercluster, 4 galaxy clusters. It's about 700 million light years away, about 3 million light years across. There are lots of good references to, if you want to learn more about the myth and lore of Hercules. I find it rather fascinating. And of course, we like to look at Hercules because, as I mentioned before, I really like looking at globular clusters. And I'm not quite sure, I don't have my object list here because I can't read the monitor. So the first object I'm going to talk about is Messier NGC 6405, is an open cluster referred to as the butterfly cluster. And this is a photographic image of it. And I got to admit, it's the first time the picture's ever been better up there than it is on the monitor. That's amazing. Okay. There are lots of younger blue stars here. And of course, open clusters by definition are going to have younger stars because gravity hasn't yet had an opportunity to rip them apart yet. Very pretty to look at. And we could probably picture a butterfly in this. And this is looking at it in the region of sky. And it's an interesting region of the sky to look at simply because of all of the nebulosity that surrounds it. Which is not, again, not unusual because it is a younger grouping of stars, which means it formed from gas clouds somewhere. So a little bit of information about Messier 6 for you go to a star party and want to impress students with your knowledge. It's about 1,600 light years away. It's about a brightness of a little over 4. So you're definitely going to be able to show it to people within your telescope. Parent dimension is about 25 arc minutes. Again, close, not quite as large as the moon, which is our 30 arc minutes. Actual diameter is closer to 12 light years. It's less than about 100 million years old. Metallicity, which means the information tells us information about the gas clouds that it was made from, is slightly larger than that of our sun, which simply says it's from a further generation. So you've had more supernovas creating more materials, metals in particular, that are used now in the gas clouds that form the stars. About 120 members of the of the butterfly cluster. Burnham called it a charming group whose arrangement suggests the outline of a butterfly with open wings. Reasonably good, good explanation of that. Okay. Sorry, I'm going the wrong direction, aren't I? Okay. I don't see anything. No, it's mostly the grapho. Yeah. Okay, so Messier 7 is an open cluster in Scorpius. And so here is a couple of images of it. This is from NOAO. Okay, again, although it is a Messier, it was also described by Ptolemy back in 200 AD. Has many visible stars to it, but again, it's an open cluster, so not a massive number of stars. And since it's within a huge gas patch, again, it's going to be relatively young, and we're sort of getting an idea of how those stars are or were formed. Ptolemy saw it basically as part of the large nebula region. Again, that was long before there were telescopes. There are about 100 stars, masses more than 700 times that of the sun. So they are relatively large stars, so they won't necessarily live very long. They're located near the tail of Scorpius. probably quite a bit older on a scale of things, twice as old as M6, but still only about 200 million years old. And they're just under 1,000 light years away. It's about 80 arc minutes across for those 100 stars. And that's close to 3 times the diameter that we would have for the moon. In physical dimensions, it's about 25 light years across, and its brightness is 3, so you're definitely going to be able to see it. However, because it is embedded in such a large nebulosity, you are going to need a scope to really identify things. And now we're looking at M6 and M7 together, so M7 was here and M6 was over here, all within a very large gas patch, which means probably many more stars are being formed within that region. Yeah, now the pretty things, the diamond on black velvet. So let's take a look at, talk about a little bit about M80 or NGC 6093. And of course, you're not quite going to get this picture with your personal telescope. This is a Hubble picture. But again, just to sort of give you an idea of how many stars there are, how large it is, the density and compactness of the stars. This is one of the very dense globulars. Yes, all globulars are by definition dense, but the concentration is quite high in M80. Brightness is about 7. It's definitely a telescopic or binocular object. It's about 32,000, a little more than 32,000 light years away, which is about 10 arc, would convert to a diameter of about 10 arc minutes. So about 1/3 of the size of the moon, which actually corresponds to about 95 light years across. More than 300,000 stars, but somewhere in that ballpark. There are a lot of bright blue stars. So these are much younger, obviously, than the cluster itself. Globular clusters tend to be some of the oldest objects in the universe. Basically, there's a high collision rate among the member stars. So the stars collide with each other, break each other apart due to gravitational effects, creating the energy and the gas that can then form newer and younger stars. So again, just looking at another picture of it within the sky. So like most globular clusters, there are of course exceptions. It's sort of sitting by itself. Okay, so our next couple of objects are going to be Messier 10, 14, and 62. And are you guys done counting the votes? Okay, so I will probably stop after these, okay? Just a couple more Messiers, though. So here's Messier 10. Here's some information about the pictures. And again, this was taken by amateur astronomers using a CCD camera, 2-color composite image. And this is a NASA picture. You can definitely see lots of clumping in that one. But it is a nice cluster. Brightness is about 6.4, more than 14,000 light years away. About 2/3 the size of the moon in a telescope, which corresponds to about 83 light years across for the whole concentration. But the bright central core is about 35 light years across. There are very few variable stars within this region, which is somewhat unusual. The total mass is about 200,000 times that of our sun. Messier described it as a nebula without stars. It was Herschel who was the first one to actually resolve the individual stars with that little, that little backyard telescope he had. Nothing personal, Brad, but it was a little bit better than you and I have. Just a little. All right, so Messier 14, and again, NOAO image, nice and pretty. This is another globular cluster. However, this one is much more spread out, so much looser, not anywhere near as dense as we saw previously, as in with M80. Brightness is about 7.6, which is fairly typical for globulars. Luminosity is about that of 400,000 times that of our sun. It's about 30,000 light years away. Again, to us, it would appear to be about the same, about a third the size of the sun if we looked at it in a telescope, which corresponds to a physical size of about 100 light years across. It has a significant number of variable stars, at least 70 of them that have been recorded. There was a nova there in June 1938, but nobody knew about it until 1964. Somebody started looking back at those old photographic plates, and they said, hey, gee whiz, this was there and now it's not. So, so keep your old photographs. Somebody else might find something of it. The Hubble telescope can't find the remnant or the nebula. So it was there in 1938, seen in 1964 in those old plates, but the Hubble has not been able to see it. Okay, and there's what we're looking at. Nice. Yeah, I like globular clusters. Okay, so we will finish up with Messier 62 or NGC 6266, two mass picture. I like those because I worked on some of the instrumentation for two mass in a previous lifetime. Visual brightness is about 6.5, it's about 22,000 light years away. This one is going to look about half the size of the moon in your telescope, which also corresponds to about 100 light years across. Again, the scaling is simply the distance. Very irregular in shape. It has a very, very dense core. It has probably already undergone a collapse, a core collapse of the cluster. It's very close to the galactic center, and it has about 89 known variables. Chandra X-ray Observatory has seen many X-ray binaries, and like most globular clusters, it is quite old, about 12 billion years old. Okay, and 8:30 is the time I'm supposed to be finished by, so thank you all very much, and I will see you again next time.
Okay, we will do questions for Mary. Are there questions on Facebook? No questions? Okay, do we have questions in our audience here for Mary? Okay, great. Thank you so much, Mary. We always appreciate your presentations. Thank you. Okay, I think Doug, you have a couple of awards. So Doug Smith, our Astronomical League coordinator, has a couple of awards that he's giving tonight. Okay, has one award for Astronomical League.
Pete Hermes, come on down. So Pete got his award for observing carbon stars. So he gets a pretty certificate.
Thank you, sir.
And he gets a pin to go with it.
Appreciate it. Thank you.